In this video I'm going to show you how our night sky would look like if we had some in-between planets. You already know if you're looking at these planets, these are not real existent planets, but I named them like in-between planets because they are placed in between real existing planets, like here Jupiter. This here Jupiter, you know, it's a real existing planet, but you probably see that like Sun-Mercury, that is not a real existing planet. The textures are taken from real planets, but they are not real existing, like I've said before, and that is the name of the planet. The type is of course planet, and the magnitude is the visual magnitude. The lower the value is, the brighter the planets are. The absolute value is about, if you're looking at that planet in 1 astronomical unit distance and it's illuminated 100%, so there is no phase angle. It's 0 degrees. And right extension declination. What most important things are elongation. Elongation, it means the distance between this planet and the sun. And the illumination shows how much part of the surface apparent from the Earth is illuminated. Distance from the Sun, these values are a bit changing because I've given in some elliptical orbits. If we are looking time forward, there is the time passing forward. So you see the distance between the Sun and this hypothetical planet is changing. But now we are looking at Sun-Mercury. That planet is placed in between the Sun-Mercury, and its semi-major axis is exactly half of the semi-major axis of Mercury. So that means that I'm using these properties to calculate the semi-major axis and also deriving the orbital periods from a third Kepler law. So that is the sidereal period. It's a period, how much time does it take to orbit the Sun once. And the synodic period is the period in between two conjunctions with the Sun. For example, here there is a conjunction. This planet is behind the Sun, and for the next time, this time, that is also a conjunction behind the Sun. I would call it like upper and lower conjunction, but this time I've looked at two upper conjunctions. So the planet is behind the Sun. In inner planets like Sun-Mercury, that's Mercury, and also Mercury is of course a real planet, and there's also Mercury-Venus, looking like that. But if you are looking at the sidereal period, it's increasing. It's also, these values are of course derived from the third Kepler law, normalized with Sun and Earth distance to 1 astronomical unit, and also to 1 year of orbiting time from Earth to Sun. The third Kepler law means that the second power of the orbiting periods and the third powers of the semi-major axis are in the same ratio of two planets. And these values for the semi-major axis, I've looked after the values from Wikipedia and so on. I've built the mean in between two planets to calculate the semi-major axis, and there you will get the orbiting period of this hypothetical in-between planets. We can look at the closest planet, and we are going more to the outside. Now, Sun-Mercury is a planet, of course, that's even closer to the Sun as compared to Mercury. So the elongation is not that much. The maximum elongation. You see this value here is about, I'm looking. Elongation is about just a bit lower than 12 degrees. And it's also dichotomy. So it's a bit about 50% illumination means in Greek, at the Greek word dichos, two, and tomis, divided. It's divided in two halves. One half is illuminated and the other half is in the dark. It's now 50% illuminated. It's like a very small half moon. The apparent diameter is about 6.7 arc seconds. It's very small. Well, in comparison, the moon has an apparent diameter of about 30 arc minutes, and 1 arc minute are 60 arc seconds. So it's very small. But now I'm looking for Potsdam in Germany. So it's about 52.4 degrees northern than the equator. So the ecliptic in the evening is not that steep. It's a rather low angle in between the horizon and the ecliptic. The ecliptic is the apparent path of the Sun. You look at the Sun is taking this path. If you are projecting this path of the Sun towards the night sky, that is the ecliptic, and now it's a very bad time to observe this planet, Sun-Mercury. But it's rather bright. Negative 2.9 is rather bright. It's about the maximum magnitude that Jupiter and Mars can get. But you are looking at this planet, you will see a bit of retrograde motion after lower conjunction. And now the best time to observe, because it's in the morning, the ecliptic angle relative to the horizon and northern half of the Earth is rather high, so it could be possible to observe this planet. Yes, it could be a bit difficult to observe, but thanks to its high whiteness, it could be possible. Remember, this planet is not a real existent planet, and you're looking at this value. It's a rather high orbiting velocity of 72.1 kilometers per second in comparison of the Earth. The Earth is orbiting about the Sun with about 30 kilometers per second, so more than twice as fast. And what you also see is Venus has also an observing period in the morning, but Sun-Mercury only a few days. You're looking 1 week later. It's almost in the upper conjunction. Yes, that is in upper conjunction, and every 34 days you will see a lower conjunction. So it could be possible to observe more than one transit of Sun-Mercury each year. For example, here is a transit, but the coverage of the Sun is less than 0.005%. So there's 0.00. It's rounded down to 0.00. So It's very low. There is a new Sun Mercury, if you are dividing that from moon phases. And now you can easily see the retrograde motion of Sun Mercury. And I'm looking after the next time there would be a transit. It takes some months, but I'm thinking about, with these days I've given it to this planet, you could observe 2 transits at least each year. For example, here in June 2026 it would be one, and also later on and also here in December that would be 2 transits a year, because of these rather close distance to the Sun and the relatively frequently appearances of lower conjunctions. So that is a very hot, should be a very hot planet, and this diameter is about the same as Mercury. And now we are going over to Mercury-Venus. Mercury, of course, is a real planet, so we're going to Mercury-Venus. I've chosen the texture of Venus, and also has some phases, and this apparent diameter goes up to about a bit more than half a arc minute, so it's bigger than Mercury has in lower conjunctions, about 12 arc seconds. Here they're looking about 33.7 arc seconds, and the sidereal period, so one period about the Sun, takes about 153 days, and the synodic period is a bit longer. It's also because you have to consider the Earth motion towards the path, and that the Earth is orbiting around the Sun, so the Sun is apparently moving away. So this difference is getting higher, and this equator diameter is lower than Venus ones, but bigger than the diameter of Mercury. And this planet can also be very bright, -5 magnitude. It's even higher than the maximum magnitude that Venus can achieve, about -4.9. But this planet has less lower and upper conjunctions. But transits are also possible, but they are a lot rarer in comparison. If we're looking, there is not every year where you can observe a transit. For example, here the Sun is barely missed by, I think it's about 15 arc minutes. The Sun's apparent diameter is about 31 arc minutes. There, 31.45 arc seconds, so 31.75 would be, if you're converting the seconds to a ratio of 1 minute. But this planet is in between Venus and Mercury. If you're looking at Venus, there is the Venus, and there Mercury. Mercury is faster than Mercury-Venus, of course. You see, there. Mercury is going back to the Sun, then Sun-Mercury, and then, of course, no, Mercury-Venus, and then Venus. So Venus is a bit slower than Mercury-Venus. So you can see Sun-Mercury is faster than Mercury, and Mercury is, of course, faster than Venus. But Mercury-Venus is also faster than Venus. There you can see that's also a new apparition. So you have a lot more conjunctions in between some planets, hypothetical and also real planets. So you are looking at 3 planets, whether close placed to each other, but only one of these planets here is real existent. But it's interesting to see the phases are changing and also the apparent diameter. It's like the same effect as you can also observe at Venus. The maximum here is about 29 arc seconds, and then it's going down again, and 50% illumination about here, and you have 16 arc seconds of apparent diameter. It's going smaller again. So you have a lot more conjunction in between and involving some more planets. I can take a look at the Sun. There you can see some of the orbits of the planets. And they also have some inclination. I've put that in to let it in a bit more realistic. And now you can observe some of the inner planets relative to Earth. So these planets have a semi-major axis that's lower than 1 astronomical unit. And we have already observed Sun-Mercury and Mercury-Venus. Venus is the next planet, and this planet is real existent. So we can now go over to Venus-Earth. Venus-Earth is right here to be found. This planet is also in the planet, so you can also observe some phases like that. And this radius is about the radius here is to be found here, 12,400 kilometers. It's a value in between Earth radius and Venus radius, and also applies to the diameter, which is shown here. The diameter of the Venus is about 12,100 kilometers, and the Earth diameter is about 12,700 kilometers. So that's also a value in between. And also the sidereal period is higher than Venus one, about 225 days, and Earth period is of course 365 days, and the synodic period is a lot longer than the sidereal period because these values are rather similar. You know, I can give it a formula in which it's shown up. The synodical period is proportional to 1 over the sidereal period of one planet minus 1 over the period of the other planet. So this difference is going to be very small because that is a denominator. The value is going up. So there is a rather high synodic period of more than 4 years. Comparison, Venus has a synodical period of 584 days, so that's more than twice as long. And this elongation of this planet can get a lot more compared to a Sun-Mercury. Here in the lower conjunction, when the planet is placed in between the Earth and the Sun, and you can see the apparent diameter is rather high, more than 2 arc minutes. It could be possible to observe a bit of the phase with the naked eye. Not of course here, but I think about that. About 2 arc minutes should be possible to observe it. The naked eye. Scorpion. And there you can see this planet is moving rather far away from the Sun. The elongation is getting very high, more than 61 degrees. 61 degrees. That is also higher than maximum elongation of Venus. I think that it should be about 46 or 47 degrees in maximum. And there's also illumination about 50% right now. Also a phase like a half moon. And you have still a apparent diameter of more than 32 arc seconds. In comparison, the Venus has an apparent diameter of about 24 arc seconds in that phase state. So rather far away, if you're looking at the Sun and Venus Earth, it takes lots of time to get back to the Sun. If you're looking here, it's slightly faster moving than the Sun. In comparison, you will see Sun-Mercury is a lot faster. There are some planets meeting each other here. Mercury, Venus is moving. These two planets are rather close located to each other. And then, of course, I've explained a bit about Mercury-Venus. Now it's going to Earth-Mars. Earth-Mars is a planet in between Earth and Mars. You can see it like there. This planet has a sidereal period of 518 days, about a bit lower, but the synodic period is also a very high value, higher than synodic period of Earth compared to Mars. It's about 780 days between Earth and Mars. And here, if we're looking at the magnitude, it's also getting rather high, higher than the maximum magnitude of Earth observers just shown by Mars. Mars' maximum magnitude is about -2.9. These magnitude values are changing a lot. So it's here where it's right about +1. And here you can see the Sun is a bit faster than this planet, and also there is the Mars moving a bit slightly slower than compared to Earth. Mars 1.5 about a positive magnitude. Now it's increasing again, but now you can see this planet is faster than Mars. And you can see there's another opposition approaching. The prograde motion is getting slower. The brightness is going to increase, and now it's retrograde motion, -2.3. We have another opposition with about -3.5. So these values are also changing because Earth-Mars also has a elliptical orbit. And now you can compare the speeds of Venus, Earth, and Earth-Mars. So now it's about longest elongation of this planet, this inner neighboring planet. And it can also be that case that only about 78% of the planet is illuminated, observed from the Earth. For example, you're looking here, the illumination is about 80% decreasing, 77%. It's rather low possible value for an outer planet, because this planet is orbiting around the Sun outside of the Earth orbit, Earth-Mars. And now we are going to go to Mars-Jupiter. Mars, Jupiter is the next planet to be observed. Here you can see it, Cancer. This planet is in between Mars and Jupiter, so it would be a planet in the asteroid belt, but Jupiter's gravitation has caused that there is not a big planet. So it's just a hypothetical planet. And here you can see it's getting rather close to Spica. It's the brightest star in Virgo. That is the constellation Virgo. And you can see that it's moving slower than Mars. And it takes about 6.17 years to orbit around the Sun once. Jupiter has a period of about 11.9 years and Mars has a period of about 1.8 years. So it's also in between this one. And the equatorial diameter is also in between Mars and Jupiter's one. Jupiter has about 143,000 kilometers diameter in equator, but Mars only about 6,800 kilometers. So that is a rather high difference because Mars is a terrestrial planet in the inner solar system and Jupiter is an outer planet which is a gas giant. Mars Jupiter is also very bright, negative 2.7 here. Maybe you can see a comparison of the apparent speed of Mars Jupiter compared to Jupiter. So we can see it's a planet in between Mars and Jupiter. There's Jupiter. Yes, you can see lots of inner planets are orbiting around the Sun. 3 more than usual. So there would be lot more conjunctions every time the Sun is passing by. And there you can see Mars Jupiter is in opposition later on that than compared to Jupiter. The Moon, you can see the Moon is passing by rather often, and here almost an occultation. Only a few arc minutes are missing. Observed from Potsdam, maybe it could be rather more to the north that occultation is occurring there. And then Jupiter is, of course, the gas giant and real existing one. And then you're going to go to Jupiter-Saturn, the planet in between Jupiter and Saturn. You're looking at that planet. It has an equatorial diameter of about 130,000 kilometers. It's also in between Jupiter's and Saturn's one. It's a rather big planet. It's looking like Saturn without rings. And the orbital velocity is also decreasing if you're going more and more out, and the sidereal period is 20 years compared to 12 years of Jupiter and a bit more than 29 years of Saturn. And the synodic period is getting closer to 1 year. And now you can see that Jupiter-Saturn is a planet which has an apparent magnitude of about 0 and a bit negative, so it's a bit brighter than Saturn mostly, but not as bright as Jupiter. That is also a property which I've tried to type in for the hypothetical in-between planets. This planet is orbiting about the Sun in 20 years. And the apparent diameter is also changing a bit if you're looking at that. In opposition it gets the maximum, in conjunction it gets to its minimum. The orbital period is about something about 11.2 kilometers per second. You can see that. So Jupiter-Saturn is slower than Jupiter, but it's faster than Saturn. Maybe I can see Saturn. Maybe I see Saturn or something. There's Saturn-Uranus. There's Saturn incoming. So you can see Jupiter-Saturn is a bit faster than Saturn. And now I think it's time to go to Saturn-Uranus. The apparent magnitude is about 2.5 in positive. So it's less bright than Saturn, which have apparent magnitude about 2 point something higher, so it's about 0.5 to about 0 for Saturn, and Uranus has apparent magnitudes of about 5.5 to 6, so it's also in between. And the sidereal period is given with 54.4 years, and the synodic period is getting closer to 1 year. If you're going further away from the Sun, this period will get in the limit to 1 year from the upper bound. The equatorial diameter is of course a bit smaller than Saturn's one, because Saturn has a rather big diameter compared to Uranus. Uranus diameter is about 51,000 kilometers, and Saturn's one is about 125,000 kilometers. Saturn, where is Saturn? I'm looking at that. There's the equatorial diameter, 170,000 kilometers. But I've now take a look at and Saturn-Uranus, and you can see that Saturn-Uranus is of course a bit moving faster than Uranus. There are lots of planets. And last but not least, you can see there is a planet Uranus called Uranus-Neptune. It's in between Uranus and Neptune. You can see apparent diameter is very low, about 3 arc seconds. It's very small. You would just see a little disk, but you cannot see any details. It's like that, observed in a telescope. Equatorial diameter about 50,000 kilometers. Uranus and Neptune are almost equal in size. And it's also going while further away, 122 years compared to about 84 years of Uranus and 165 years of Neptune. And this period is getting rather close to 1 year. It's a bit more than 3 days. The opposition is shifted later from year to year, only about 3 days. You can see Uranus and Neptune is rather slow in compared to the other planets, and here Jupiter, Saturn, and the moon is passing very often. There's a time, and there's also some times that 2 planets are getting very close to each other. Maybe I can see a conjunction here. You can see 4 planets in a row, but one planet is, this one is hypothetical, and these 3 planets are real existing planets, but it's too close to the Sun to be observed by telescopes, so it would be at the day sky. But here Sun-Mercury is rather fast. Maybe I can see a conjunction very slow. Or was there a transit with a solar eclipse? There was a transit of Sun-Mercury, and only some hours later there was a solar eclipse. I think about in the 18th century there was a Venus transit, and only a few hours later or earlier, a bit of time difference of just above some hours, there was a total solar eclipse. So two weather rarely things to be happened in the sky. Venus transits are very rarely to observe. The last one was in 2012, and the next one will be in December 2117. It's a long time to go. There is Neptune. It's a further away planet from Earth, because Pluto is not more a planet decided by the IAU in 2006. Now, I'd like to finish this video with about observing this planet about 4 or 5 years. I'm letting that animation run just until 2027, with including this year, and I think that should be a good end of this video. So we can see whether the inner planets, 3 more than usual. Of course, Sun-Mercury is very fast, but Venus is rather slow, but Venus-Earth is even slower, orbiting around the Sun. I hope you enjoyed this video, and there is also Mars, a bit slower than the Sun, Saturn, Jupiter-Saturn, and you can also see Earth-Mars right now, Jupiter-Uranus, Venus, Earth-Mars, it's rather close, Mercury-Venus, Mercury. It should take a bit time to get to the other side of the Sun. For Venus-Earth, you can see it's orbiting rather slowly compared to our Sun. Compared to the Venus, it's a bit slower too, but it's very slow compared to Sun-Mercury. So I hope that you enjoyed this video. If you want to know a bit more how I done that, I can say that this program which I use is Stellarium, and I've modified this file solar system as system minor. I've typed in some more values for planets, and as I've said, I've derived them of taking the mean of 2 real existing planets and then also derive from the third Kepler's law the orbiting periods. So these values should be a bit more realistic. And now I think after this year is getting to the end, 2027, I would say that should be the final point, and I hope you like that, and see you next time.